Have you ever wondered what is the smallest possible length in the universe? It's a question that challenges our understanding of reality and pushes the boundaries of human comprehension. This elusive length is known as the Planck length, named after the physicist Max Planck, who contributed significantly to the birth of quantum mechanics. Now, just how small is the Planck length? Well, let's put it this way. If we were to magnify an atom until it's the size of our planet Earth, the Planck length would still be much smaller than even the head of a pin. That's right, it's that tiny. This comparison isn't meant to boggle your mind, but rather to illustrate the almost inconceivable minuteness of the Planck length. So let's dive into the world of the infinitesimally small and explore the concept of the Planck length. So, what exactly is this Planck length, you might ask? The Planck length, named after the physicist Max Planck, is a unit of length that's fundamentally different from others. It's not just about being incredibly small, it's about the very fabric of the universe itself. To understand the Planck length, let's first take a quick look at Max Planck, the man behind the concept. A German theoretical physicist, Planck is considered the father of quantum theory. He proposed a set of units now known as Planck units based on fundamental constants of nature. These constants include the speed of light, the gravitational constant, and Planck's constant, which relates the energy of a photon to its frequency. The Planck length is one such unit. It's approximately equal to 1.6 x 10 to the power of -35 meters. Now that's a mind-bogglingly small distance. To give you a sense of scale, if an atom were the size of the Earth, a Planck length would be a lot smaller than even the head of a pin. But why is it so special? Well, the Planck length is thought to be the smallest length that has any physical meaning within the framework of our current understanding of physics. It's the scale at which classical physics, as described by Newton's and Einstein's theories, gives way to the strange and counterintuitive world of quantum mechanics. At distances smaller than the Planck length, our conventional ideas about space and time start to break down. It's here that we enter the realm of quantum gravity, where space and time are thought to be quantized, or broken up into discrete chunks. So, the Planck length is not just a unit of measurement, it's a frontier, a boundary beyond which our current theories cannot venture. It marks the edge of our understanding of the physical universe, the point where the known meets the unknown. In other words, the Planck length is the scale at which classical ideas about gravity and spacetime cease to be useful, and quantum effects dominate. Now that we've got a grasp on what the Planck length is, let's delve into its significance. The Planck length, as we've just learned, is the smallest theoretical measurement of length that has any meaning. It's named after Max Planck, the physicist who first proposed this quantum theory. The Planck length is roughly 1.6 times 10 to the power of -35 meters. In simpler terms, if an atom were the size of the Earth, a Planck length would be much smaller than even the head of a pin. But what does this extreme smallness mean? Why does it matter? Well, the Planck length is believed to represent the limit of the smallest possible event or thing that can exist in the universe. Below this length, the very idea of space-time as we know it becomes irrelevant, and the laws of physics as we currently understand them cease to apply. The Planck length plays a pivotal role in theories of quantum gravity, including string theory. Quantum gravity is a type of theoretical physics that seeks to explain the force of gravity according to the principles of quantum mechanics, which is the branch of physics that deals with the smallest particles in the universe. The Planck length is essential to these theories because it sets the scale at which quantum effects become significant for the study of gravity. Meanwhile, in string theory, the Planck length is considered the size of the strings that are the fundamental constituents of matter and forces. These strings vibrate at different frequencies, and each frequency corresponds to a different particle. So even though these strings are unimaginably small, they're responsible for all the diverse particles we see in the universe. So, while the Planck length might be unimaginably small, it's a big deal in the world of theoretical physics.